All right, good morning. Happy Friday. All right, yesterday in period 2, we had a major problem with WebEx. I thought it was my problem. I'm glad it wasn't. I actually got a message. I was having audio video problems. So I ended up not teaching period 2. So those students are going to have to watch the lesson on YouTube to get the lesson. Later on in the day, I got a message from the district saying that it was a technical problem. So it'd have been nice to know that, at the beginning, but I'm hoping, the reason why I'm telling you this, I hope we're not gonna have any problems today. If we do though, I will be sending a remind message. So it's important to have the remind app. Anyhow, we're gonna continue with the lesson here in 5.2. So we talked about some things the other day. We talked about different polynomials and the names of them. We talked about the leading coefficient, the constant term. So we looked at classifying polynomials. We also talked about how the degree of the polynomial actually tells you the number of solutions. So it tells you the number of roots, tells you the number of zeros. So we also talked about multiplicity. And the reason why we're talking about all these things is it's going to help you to graph. They're not going to say, what is the degree? What is the leading coefficient? What is the constant term? What is the multiplicity? Those are all things that you're going to use to help you graph, like the in behavior. So we looked at when you have an odd degree function, its in behavior goes down and up, like the cubic. We also looked at the even degrees and how they go up on both ends. That tells you that it's an even degree tells you that the in behavior goes up on both ends. So all of these things you're going to use to help you out. Okay, anybody want to ask me any questions about what I've talked about so far in 5.2? Questions about 5.2? All right, I'm going to continue on then, and guess what? I have no markers. So I had to pick up everything yesterday, so my markers are out in the garage. So hold on just a second, I'm going to get the markers. Sorry about that. Forgot all about those. Kind of important to have the markers, right? So I have them now. Sorry. Okay, so I want to talk about maximum minimums, but specifically global maximums, also known as absolute maximums and minimums. And we're going to talk about local maximums and minimums, which are also called relative maxes and mins. So let's write down a bunch of definitions and we'll look at some examples. All right, so a global maximum is the point on the graph which has the largest value y. So it's a point. Are you guys there? I'm scared from yesterday. Are you guys there? Anybody there?
Yeah.
Yep.
Yeah.
Okay, thank you. Thank you. It's good to hear you guys. The point on the graph that has the largest value of y, and then a global minimum is a point on the graph that has the smallest value of y. And like I said, these globals, sometimes in higher level math classes, they call them absolute. So then we have local maximums. And plural, this would be local maxima. Maximum is singular. So a local one would be the point or points, there could be more than one, on the graph. Which have maximum y values relative to the points close to them. On the graph. And then we have local minimums. So plural, it would be minima. Minimum is singular. So it's the point or points. Which have minimum y values relative to the points close to them. Oh, a lot of writing. Can you guys see all that? And these are sometimes referred to relative maximum and minimum. So like I said, sometimes you'll see the word global or absolute. Other times you'll see local or relative. All right, let's take a look at some graphs. And this seems, it's really easy, but there's something weird that's going to happen at the end. So here's a graph. And remember the definition of turning point. It's where a graph changes, it's a point where the graph changes direction from increasing to decreasing. That would be a maximum. And a minimum would be a point where the graph is changing direction from decreasing to increasing. So we're specifically looking at that point, and that point. And so you could probably guess this is a global maximum by definition. This would be a local maximum. And that guy right there, he's a local minimum. So pretty easy. The next graph looks like this. By the way, that first one was a quartic that was reflected over the x-axis. And this one right here, this is a cubic that's been reflected over the x-axis. So on this graph, we're looking at those 2 points, and this would be a local max. So if you thought it was a global, it's a local, and this guy is a local minimum. So far so good, pretty easy. that one. Okay, on this graph, you have two that are at the same spot, and then you have this guy here. So this would be a local maximum. This guy would be a global min and a global minimum. By definition. So this was a quartic. This is also a quartic because it looks like a W. There's 3 turning points. There's also 3 turning points here, but a little bit different. So once again, this is a local maximum. These are not at the same depth. So this guy would be a global minimum, and this would be a local minimum. Okay, now this is the one I want you to look at. Okay, look at this one. Okay, this guy has 1, 2, 3, 4 turning points. So I'm thinking that this is probably a quintic because it has 1 less turning points in the degree. And pay attention to what I'm going to write here. All right, this is a local max. And this is also a local max. And you probably thought that was a global, but it's not. This guy is a local min, which you probably figured. And this guy is a local min. So what's going on? So everything was easy there for a second, and then it just all fell apart because, like, what's going on here? All right, I'm going to clear it up. Because like me, you probably thought that this was a global max, a local min, and a global minimum, but it's not. So I need to say something that makes sense. So here it is. Now, I'm not talking about odd functions. I'm talking about odd degree polynomials. So with odd degree polynomial functions, there are no globals. So that's it. So with odd degree, like x cubed, x to the 5th, x to the 7th, there are no globals. So there are no global maximums. And this right here, remember we said we thought it was a quintic because there's 4 turning points. And then I'm going to make one more comment. You can only have global maximum minimums with even degree polynomial functions. So that's what happened over here. All right, any questions about that? Okay, so now what we're going to do is we are going to sketch some graphs with all this information that we've accumulated. So they're just going to say sketch. And you're going to have to know, hey, what kind of tools do I have to do these sketches that they're requiring without making a table of 50 values? And by the way, you cannot put these on the calculator. You can to check yourself, but on a test, if you just put them on the calculator and graph them, I'm going to mark them wrong. You have to show all the work. So I'm going to say that again. You can put these on the calculators to check, but you must show all this work if you want credit for it on an exam. So they're going to say, sketch the graph. That's given in intercept form. So remember, intercept form is the same as factored form. So they're going to give you a function in intercept form. And you're going to have to use some tools to figure out what are we going to do. So how about find the in behavior? So what is this thing? Is this a quadratic, a cubic, a quartic, a quintic, a 6th-degree polynomial? What is it? So you want to look at it and tell what this is. What is it? If you multiplied all that out, what would you have? Go ahead, I'm listening. We're not going to multiply it out. If you multiply this x times that x times that x, what is it?
Would it be a cubic?
Yeah, it's a cubic. So you know it looks something like that. So you can guess the in behavior. So what's happening on the right? The graph is going?
It's going down.
It is on the right?
Oh, I mean up.
On the right?
I mean up, sorry.
Okay, that's okay. What's it doing on the left? Class?
Now going down.
Yeah. Okay, so that's the first thing we want to know, because when we go to do this graph, this is very, very important. So now you know the use of the in behavior with the higher degrees. We know that it's going up on the right and down on the left. Okay, the second thing we want to do is we want to find the X-intercepts, or the zeros. So what are the X-intercepts? I don't know, look at this. What makes that 0? Come on, what makes that 0?
0.
What makes that 0?
-2.
What makes that 0?
-3.
Okay, now your book teaches this really weird thing, and I have it on my notes to teach it. I'm like, I'm not going to teach it. It's dumb. I'm not going to teach it. Because what we're going to do right now is we're going to look at the multiplicity. So remember the multiplicity? That if the root appears an odd number of times, it crosses the x-axis. If it appears an even number of times, it touches and turns or is tangent. That's what we're going to do. All right, here we go. So each one of these occur once, right? So we would say at 0, it occurs once. So does it touch? Is it tangent or does it cross? We talked about this, didn't we?
It crosses?
Yeah, we talked about this, correct? Okay, -2 occurs once. Does it cross or is it tangent?
It crosses, and so does -3.
Yeah. All right, we're ready. So we just did this on our own. We know what's happening at the ends of the graph. We know what the roots are, 0, -2, and -3. Did I write that down right? I didn't write it down right. Good. I'm going to cross that. This is a minus, which makes that a positive 3. So better. Okay, so it would be a positive 3, positive 3. Okay, and then we just graph it. So we're going to start down here. And what do we do at negative 2? We cross. What do we do at 0? We cross. What do we do at 3? We cross. And voila, there's your graph. Now, here's the deal. This is a sketch. So we don't know how high this goes or how low the valley is, but it looks something like that. So that's a very good sketch of what this looks like. And like I said, you must do this work by hand. If you put this on the calculator, I'm not going to give you credit for it. So you have to show this by hand. Pretty cool, right? I mean, we just graphed a pretty complicated function by just looking at the end behavior, the x-intercepts, and the multiplicity. The book, let me just tell you what the book says. The book is wanting you to show the intervals of positive and negative. So it's wanting you to show that from negative infinity to negative 2, it's below. From negative 2 to 0, it's above. From 0 to 3, it's below. And from 3 to infinity, it's above. But big waste of time. Let's just do the multiplicity. And I'm going to try not to give that book stuff. I got to pay attention to the exam. You guys want to ask me about this before I erase it? But I got to make sure on the exam that I don't give you anything the book is doing. It's a big waste of time. It's ridiculous anyway. They're trying to use positive and negative, and they're not using it in a great way, so why do it? All right, let's do another one. All right. See how smart you guys are. All right. First of all, do you think this is a quadratic, a quintic, a quartic, a 6th degree, 7th degree? If you multiply this all out, x times x times x times x, what do you think you would have? So this is an intercept form. It's also called factored form. What do you think this graph looks like? What kind of polynomial is it?
A quartic?
Yeah. And then here we go. You see that negative? What do you think that does to the graph?
It reflects it.
Yeah. So instead of looking like a W, it looks like an M. That's exactly right. All right. So now that we know that it looks like, we can write the end behavior as x goes to the right forever. The function is doing what? As x goes to the left forever, the function is doing what? So as you go to the right, what's the function doing? As you go to the right, what is the function doing?
It's going down.
Okay. As you go to the left, what is the function doing?
It's also going down.
So when we go to do our sketch, you better be going down on the ends, right? All right. Well, what are the x-intercepts? So what makes that 0? Hello?
+4,
What makes that 0?
+1,
What makes that 0?
-1,
What makes that 0?
-2,
Yeah, okay, now, each of those occur once, right? So the multiplicity is 1. Yeah, so what's happening at 4?
It crosses.
Yep. What's happening at 1? What's happening at 1?
Crosses.
Yep. So it's crossing at all these, right? So let's just think about this for a second. We think that the parent is a quartic. That means there's at most 3 turning points, 1 less than the degree. We have 4 solutions. Let's graph the zeros. So write 4 zeros a solution, write 1 0 as a solution, -1, -2, and we're ready to graph. So we're going to cross through -2, we're going to cross through -1, we're going to cross through 1, we're going to cross through that. Now, like I said, we would have to investigate more to know how high this is or how low, but this is a really good sketch of the graph. That's a really good sketch of the graph right there. All right. Do you guys have questions? You want to do one? You want to do a hard one? Want to do one more?
Yeah.
Okay. I'm just going to make this one up. You guys are going to answer. Okay. I like this lesson because it's a powerful lesson. You can just look at graphs and know what they look like without doing a whole lot of work. Okay. So what do you think the degree of this guy is? What's the degree of this polynomial? Is it a quadratic, a quartic, a quintic, 6th degree, 7th degree, 8th degree, 9th degree polynomial? What is it?
It's a 7th-degree polynomial.
Yeah, it's a 7th degree. So 7 tells me that it goes down 1 turning point, 2 turning points, 3 turning points, 4 turning points, 5 turning points. One, 2, 3, 4, 5, 6. There we go. So it could look like this, right? So for sure it goes down and then up because it's odd degree. There's at most 1 less turning point, which would be 6. And what's that negative mean?
It reflects.
Yep. So it does this. One, 2, 3, 4, 6, right? You guys okay or not? Unmute yourself and tell me, are you okay or not?
Yeah, I'm okay.
Yeah, we're okay.
Okay. Only 2 people?
I'm good.
Okay. All right, here we go. So what's the end behavior? As x goes to the right, what's the function doing?
Going down.
As you go to the left, what's the function doing?
Going up.
Yep. All right. So what are the x-intercepts? What are the roots? What are the solutions? What are the answers? I don't know. What makes that 0? This is x times x, right? What makes x 0?
0.
How many are there?
There's 2.
Because of the power. Okay. What makes this 0?
Positive 1.
How many are there?
3.
Yep. And what makes this 0?
Negative 2.
That's right. And remember, in a set, I wrote it like this so you could see the multiplicity, but in a set, you only write the roots once. Right? All right, here we go. At 0, we have 2 of them. So what's happening at 0? Is it crossing or is it tangent?
Tangent.
And tangent means it just touches and turns, right? What's happening at 1? It's an odd number, 3. What happens with an odd number of roots?
It crosses.
Yeah. And negative 2, it's an even number, right? I'm not talking about the number itself. I'm talking about the number of times it occurs. So 0 occurs twice, 1 occurs 3 times, and negative 2 occurs twice. What does that mean?
Tangent.
Yeah. All right, let's see what this thing looks like. So let me graph the roots first. So we have a root at 0, 0, at right 1, 0, and at negative 2. So we're going to hit negative 2 first, right? Because we're going from left to right to graph. So what's happening at negative 2? Tangent. Hello? What's happening at 0?
Tangent.
What's happening at 1?
It crosses.
So see that? Now we're only seeing 4 turning points, but we don't know what's happening. I mean, this could have like a little dip in it. 2 little dips, who knows? So we don't know, but this is a good sketch of the graph, and we're seeing 1, 2, 3, 4 turning points instead of 6, but that's okay. So this is really close. So we have at most 6 turning points, and we're only seeing 4. 1, 2, 3. That's a good sketch. Okay, any questions about this before we go on?
No.
Pretty cool, right? You don't have to make a table of 50 values. We can get a really good idea about what this graph looks like very quickly. All right, now we're going to actually do an application. And we're going to use the lid of a box. So I'm going to show you. My kitties have a sushi box. See their sushi, tuna. Fish. All right, what we're going to do is we're going to cut the corners of this box and lay it out. So I'm going to draw a picture of it. And what we're going to do is we're going to find out the maximum volume of a box. Let's say a company, they want us to design a box with a maximum volume because they don't want to spend money on 2 boxes. So they want a maximum volume to hold whatever they're making. They want to hold a maximum number. So they want to know the maximum volume. All right. For those of you who are interested, I'm on page 255. Page 255. And if you noticed, those of you who started the assignment early, I deleted the assignment out and put this box problem in. And the reason why is last year, this was on the district assessment. So this was the problem that was on the district assessment. So you can use cubic functions. Watch. Isn't volume length times width times height of a rectangular prism? Well, isn't volume a cubic? So don't write this down, just watch, I'm explaining this. Doesn't a cubic look like that? So wouldn't this be the maximum volume? So when I do this graph, you're not going to see this part, but we don't care about that part. We care about that right there. So I don't want you to think I'm graphing a quadratic. I'm not graphing a quadratic. I'm going to be graphing a cubic, but you're going to, I'm only going to capture this part of the cubic. So I just wanted to explain that. All right, so let me show you the picture here. Okay. So the length of the box is 9 inches from there to there. And the width of the box is 5 inches from there to there. Now, if we take the box apart, we have these folds that fold up to make the box. Now, the first thing we want to do is we want to define our variable. So we're going to define the variable as the length of this side flap. That's what we're going to call it. So every side is X, side flap. So that right there is the side length of the square flap. So basically what we're going to do is we're going to define the length, the width, and the height in terms of the side length of the square flap. So let's take a look at the length first. And remember what our goal is. Our goal is to find the maximum volume of the box, with the X being what? Who knows? All right. So how do we represent the length in terms of X? Well, if the length is 9 inches, couldn't you represent the length as 9 minus X times 9, I'm sorry, 9 minus X minus X? Because wouldn't the length be 9 minus that distance and that distance? So the length would be 9 minus 2X. Can you unmute yourself and tell me you understand this? Do you understand this? Okay. So the width, crash. the width would be 5 minus x, which is 5 minus 2x. And the height of the box, if we folded the box up, the height is x. Right? The height, x. So the second thing we want to do is we want to write the volume in terms of x. So the volume in terms of x, or v of x, would be 9 minus 2x times 5 minus 2x times x, wouldn't it? So they're going to ask for all this information. Okay, the next thing we're going to do is we're going to show 3 constraints and write something called the feasible domain. Constraints. Constraints means conditions that have to be adhered to. So the first constraint is 9 minus 2x, which is the length, has to be positive. It can't be negative, right? So length cannot be negative. So when we solve for x, we get negative 2x is greater than negative 9, and now we multiply by a negative. Multiply by a negative flips the symbol. Multiply by a negative gives that, and now you divide by 2. So this is about 4.5. So x, the length of the side length of the square, has to be less than 4.5. The next constraint is the width being greater than 0. So the width has to be positive also. So when you subtract 5, multiply by a negative, flip the symbol, x has to be less than 5/2, which is about 2.5. So this is the constraint for the length. That's the constraint for the width. And then we know that x is the height has to be greater than 0. So what we're going to write right now is something called the feasible domain. So what we're going to do is we're going to look at all 3 of those and go, okay, hold on. X has to be greater than 0. And it has to be less than 2.5. So it can't be less than 4.5 because that condition couldn't be met. So the feasible region is based, see, this guy will fit in the 2.5, but the 2.5 won't fit in the 4.5. So the feasible domain in interval notation is 0 to 5/2. Okay, now you're going to need your calculator. I'm going to show you how to set up the window. I got to erase this. You guys have this written down. Listen carefully. I'm going to try to explain this clearly about how to set up the window. And then we're going to use the second calc feature to not do an intersection, but to do a maximum.
Ms. Birch, I have a question. Why are you flipping the sign on the third?
The symbol?
Yeah, the symbol.
When you multiply both sides by a negative, you always flip the symbol.
All right.
So the rule says that if you multiply or divide both sides of an inequality by a negative, you have to flip the symbol.
All right. Thank you.
All right, so check this out. We have to be able to define the window. Remember X min, X max, X scale, how are we going to count? Y min, Y max, Y scale. Well, the domain helps you with the X's. That's why we found it. So we have to go between 0, 2.5. So I'm going to go from 0 to 3, counting by ones. The Y is another story. So the Y, you're just going to have to mess with this. I'll be honest with you. When I first did this, I went from 0 to 100, counting by tens, because I'm trying to capture the graph in my viewing window. So you have to mess around with this. And what I decided was I'm going to go from 0 to 30, counting by threes. So everybody, okay, so this is what you're going to do. Put this in the equation editor. So under y equals, put this in the equation editor and set up your window like this. Okay, I'm going to wait for you. So put this in the equation editor and set up the window. Remember, the equation editor is here and the window is there. When you're done doing that, hit graph. You should get a graph that looks like this. Can you just tell me, can you unmute yourself and tell me, yes, you got the graph, or I don't know how long I should wait?
I got the graph.
Okay. Does anybody need more time? Speak up now. Need more time? No? You have that in the equation editor and you have this in your window and you hit graph.
Wait, why did you say it was it was 3 again for the X max?
Because this went up, we said that our feasible domain was 2.5. So I just went up a little bit more.
How
I
can
don't
we,
want to do it right at 2.5. I want to be able to capture the graph. So I don't want to go right at 2.5. So I made it 3.
the window is how much it like shows, right?
Yeah, the window is what you're going to see in your graphing calculator view. Remember?
So
You're trying to capture this maximum. Now, this is not a quadratic. Like I said, this is a cubic. So this is a cubic that goes like this and goes down and then up. So we're just capturing the maximum.
What equation do we put in the calculator?
This. Parenthesis 9 minus 2x, parenthesis 5 minus 2x, parenthesis x. You put that in the equation editor. Right? Y equals. You put this in the window and you hit graph. Go ahead. Questions about the calculator? Questions? Okay, what you're going to do, you're going to go to second calc, and you're going to pick number 4, which is a maximum. So second calc is second trace. Go to second trace and pick number 4, a maximum. It says on the calculator, left boundary. So what you're going to do is you're going to take the spider with your arrow and put the spider over here on the left and hit enter. When you hit enter, it's going to put an arrow. Then it's going to say right boundary. So you take your arrow key and put the spider here and hit enter and see how it's honing in on the maximum. And now the calculator is going to say, do you want me to guess? And you're going to hit enter and you're going to tell me what you see. So what is the Y value?
The Y value, it says 21.015749.
And what's the X value?
1.0316.
Okay.
Okay.
So here's what we found. We found out that the volume is 21 when X is about 1 and so what does that mean? Can I erase this over here? Or you want to ask me a question about this, or can I erase this? I can erase this? So I just want to make sure we understand what we found. All right, we found the maximum volume, and we also found the size, the length, X, of the square flap that we need to get that maximum volume. So this means the box has a maximum volume of about 21 cubic inches when the side length of the flap flaps are of length 1 inch That's good enough. So this means the box has a maximum volume of about, that's the Y value, 21 cubic inches when the side length of the flap X are 1 inch. When the side flaps of length X are 1 inch. Okay, go ahead, I'll take questions. I did assign a sheet of these problems. The sheet is really hard to see because it's really small. So I want you to write down this information that I'm going to give you. So I'm talking about this sheet right here. So it's really hard to see this sheet, but these are the box problems. I'm going to read out this information to you in a minute. But before I do, anybody want me to go over the calculator again? Or anybody have any questions?
So in order to find the maximum, you would put the X on like the sides. Where do you say you have to put the X's?
The X's are going to be the side flaps, which when they fold up are the height, right? So you're going to let X be the length of the side flap of one of the sides. So one of the sides is X and the other one's X because they're square. So this flaps are square. So it's X by X by X by X.
Yeah, but my question is, so you see when we're graphing it, you see how up there?
Talking about the spider.
Yeah, the spider, my bad.
Oh, okay. I thought you were talking about the box. Go ahead. You're talking about the graphing calculator.
So where would you put those?
Okay, so once again, this is not a quadratic. It is part of a cubic. We're just not seeing the other part of the cubic in the viewing window. So you're going to go to second calc and pick 4, and you're going to pick the maximum feature. Okay, what it says is what is the left boundary? So you have to take your arrow and move the spider somewhere, it doesn't matter, move it somewhere on the left of the maximum. After you move it somewhere to the left of the maximum, you hit enter and it locks it in. Then it says, what is the right boundary? So you take your arrow key and move the spider over here somewhere. It doesn't matter, just move it over here somewhere. And when you hit enter, it's going to lock in that side. And now you're ready for the calculator to tell you what the maximum is. And the maximum is 1 point something, and then it was 21 point something. Right?
Yeah, I'm trying to do it right now.
Okay, other questions? Okay, last call. Any questions? All right, I need you to write this down because that sheet that I'm talking about for the box problems is so small, it's confusing, so I want you to write this down. So I'm talking about this sheet right here. On problem number 1, this length is 20 and this width is 16. On problem number 2, this length is 16 inches and this width is 12 inches. On problem number 3, they're giving you the volume in terms of x is negative x cubed minus x squared plus 6x. And they're saying that the depth is equal to 2 minus x. And in problem number 4, the length is 2x plus 3. The width is 2x minus 3. And the height is 3x. Okay, so I'm sorry that this didn't show up really good on the sheet, but that's what the numbers are, the variables. And now what we're going to do is we're going to go into the Math Wizard teams. We are not going to come back to class. I am taking attendance in there, so if you don't show up, you'll be marked absent. Class ends in about 20 minutes, but I want you to do this problem number 1 together as a group and ask me questions if you have any problems with the problem or the graphing calculator. And we will be leaving the Math Wizard teams today at 10:45. All right? All right, I will see you in the Math Wizard teams. Class is over at 10:45. All right, let me know if you need help.